This video is brought to you by mywayteaching.com.
So in this part, we are going to see the second method of the solving this problem. That is, how long will it be before ball hits the ground? So for this second part of the question, we have another method. So I already explained about the first method, isn't it? I already explained you about the first method. Let us see the second method of solving this. The total time taken can also be calculated by noting the coordinates of initial and final positions of the ball with respect to the origin chosen and using the equation, that is y is equal to y naught plus v naught into t plus half at square. Here, by noting the initial and final positions, we can calculate the time taken. So here y naught is 25 meters, isn't it? You can see in this figure also. And y is 0. V naught is given by how much? 20 meter per second. And a is given by minus 10 meter per second square. Then what is the value of t? Substituting all these parameters in the given equation, that is y is 0, y naught is 25 plus v naught is 20, and we should calculate the value of t, that is half into minus 10 t square. So here 2 ones are, 2 fives are, 25 plus 20t minus 5t square. So we can also write it as 5t square minus 20t minus 25. Isn't it? So we know the method of solving the quadratic equations. You know it, right? Yeah. In this we can take 5 common, isn't it? Then it becomes t square 4t minus 5. And I can write it as t square minus 5t plus t minus 5 is equal to 0. So if I take t common, it will become t minus 5. So here we'll get two values of t, and we are considering the positive value of t by neglecting this. So t is equal to what? Yes, the time taken is 5 seconds. So the same answer we got, as we know, we also got the same answer, isn't it, in the first method. So here the time taken is given by 5 seconds. So the next illustration is about free fall. Discuss the motion of an object under free fall and neglect air resistance. An object released near the surface of the earth is accelerated downward under the influence of force of gravity, isn't it? When you drop an object from upside, it will move towards the earth due to gravitational force. The magnitude of acceleration due to gravity is represented by g. What is this g? G is acceleration due to gravity. If air resistance is neglected, then the object is said to be under free fall. If we neglect the air resistance, then we can call it as free fall. If the height through which the object falls is small compared to Earth radius, then we can take g as a constant. The height of the object, if that height is very small compared to radius of the Earth, then we can see take this acceleration due to gravity, that is g, as a constant value, and its value is given by 9.8 meter per second square. Okay. Free fall is thus a case of motion with uniform acceleration. We assume that the motion is in y direction. Okay, we'll consider the motion in y direction, and more correctly in negative y direction. When the object falls towards the ground, we'll consider its motion in minus y direction because we choose upward direction as positive. If we throw a ball upwards, then we'll consider it as positive, and the downward direction we'll consider it as negative. Since the acceleration due to gravity is always downward, it is in the negative direction, and we have a is equal to minus g, and its value is given by minus 9.8 meter per second square. The object is released from rest at y is equal to 0. So at y, the object is at rest, isn't it? So it is released from rest. Therefore, v naught is equal to 0, and the equations of motion become. So we'll consider the initial velocity is equal to 0. So the equations of motions become v is equal to v naught, that is 0, minus gt, that is given by the value of g is we know that is 9.8 t meter per second. And the another equation of motion, that is y is equal to v naught, that is g plus 1 minus 1 by 2 at square. So here a value is a is replaced with minus g. So here we know the value of g, that is 9.8. So it is given by minus 4.9 t square meter. And one more equation, v square is equal to v naught square, that is 0, minus 2a, that is plus 2ay. So here we'll represent this a with minus g. So it is minus 2gy. Okay. And we can get the value, g is 9.8 into y. So it is this is minus 2gy. So its value is minus 19.6 meter square per second square. These equations give the velocity and the distance traveled as a function of time, and also the variation of velocity with distance. The variation of acceleration, velocity, and distance with the time, okay, have been plotted in these figures. So the first figure is variation of acceleration with time. Okay, in this we can see for a freely falling body how this acceleration varies with the time. So here this is uniform acceleration for in equal, it covers equal, the acceleration with respect to time is uniform, isn't it? So that is represented using a straight line, that uniform acceleration, and that acceleration due to gravity is given by g. Its value is minus 9.8 meter per second square. This is the first figure. And the second figure is given by variation of velocity with time. So under free fall, how this velocity of an object, whenever we throw an object, so when it falls towards the ground, at that time, how this velocity varies with the time is given in this particular graph. So here it is a straight line from origin O. Okay, this is the second case. And the third case is variation of distance with time. So here on the y-axis for a freely falling body, so all these three cases are for a free fall. Of a body. So here we have taken distance along y-axis and time along x-axis, and how this variation, the distance varies with time when an object is thrown towards the earth. So these are the three important cases. Now let us see another simple illustration, that is Galileo's law of odd numbers. That law says the distances traversed during equal intervals of time by a body falling from rest stand to one another in the same ratio as the odd numbers beginning with unity. Okay, if whenever a body is moving towards, or if a body is falling from rest, then the distance traversed by that body, it is similar to that of the ratio, it is similar to that of odd numbers when we begin with unity. Okay, in that body traverse, the distance traversed by the body is in the same ratio as the odd numbers beginning with unity, that is 1 is to 3 is to 5 is to 7. That is what the Galileo's law. So let us divide the time interval of motion of an object under free fall into many equal intervals, okay, tau, and find out the distances traversed during the successive intervals of time. Since initial velocity is 0, we have y is equal to initial velocity is 0, that is v naught is 0. So v naught plus half at square will become what? And for a free fall under, okay, when a body is falling from rest, so v naught is 0, and this a is represented with minus g, and this one is t square. So when a body falls from certain distance, we are dividing this into a number of time intervals, and we'll calculate this each time intervals. Okay, and then we'll see whether it is same as that of the odd numbers ratio. Okay, So using this equation, we can calculate the position of the object after different time intervals, that is from at 0, 2 tau, 3 tau, at different time intervals, which are given in the table. So we can see in this table the distance traversed calculated at different instants of time. Okay, distance traversed in successive intervals, that is given by y0, 3y0, 5y0, 7y0, and if we take the ratio, then it will be 1, 3. So it is the Galileos law. So we are getting the ratio of distance traversed same as that of ratio of odd numbers, isn't it? 1 is to 3 is to 5 is to 7, and it goes on.